hard. So the last little bit deals with instances where you've got, draw a little circle here. Instances where we've got two carbonyls that are basically spaced apart with there's 5 carbons between the two of them. And there's a couple of common scenarios where this would take place. Scenario A or B. And so with both of these, the strategy is going to be similar. It's just that the what's the acceptor and what's the donating group will vary slightly. So in each case, what we're going to do is we are going to make the disconnection basically here or here. And it's going to set up, we've got the idealized reagents here, this plus this, or this plus this. So the commonality is that we have got an alpha carbon with a negative charge, alpha carbon, negative charge, and a alpha beta, a beta carbon with a positive charge. So we've got the guys in orange are going to be enolates or their equivalent. And here we will have an alpha beta unsaturated carbonyl. In this case, it just happens to be an ester, and over here, this would be a alpha beta unsaturated ketone. So this would be 1,4 addition or Michael addition. So 1,4. Right. So let's do, which one do we want to do first, A or B? Let's do B first, just because it's what we can use. Okay, so I'll do another sort of thing here. If you've got an ester, so this is basically an ester, or an acid, remember the equivalent of this, so when we said enolate equivalents, can be the malonate, OR, because when you've got the extra carbonyl here, it makes the resulting negative charge softer, put that in brackets, and this promotes 1,4 addition. Yes. So our synthesis, and I guess when I put this little, technically this should be, I'll erase that. Because we're going to see in a second that I'll make that into a carboxylic acid. So as a basically as a review, if we've got our we've deprotonated this with sodium hydride or the corresponding, like we do in the lab, the OR minus. This will come in, tack there, electrons move up, electrons move all the way across. We've generated a our 1,4 addition product. And what could conceivably happen, although it might happen depending upon what the solvent is that we're using, this is going to get the resulting ester, I mean the enolate's going to get protonated, and we would have something like this. This could be stabilized. You got a stabilized enolate, or and then this will get protonated, H plus eventually, and we have our corresponding 1,4 addition product. Then the last step, which we covered last class, is if you take acid and you heat this up, we will lose the carboxylic, we need water in there. The first step will be that each one of the esters will get hydrolyzed to the carboxylic acid, and then that gets decarboxylates, and our final product would look like this. And we've got 1, 2, 3, 4, 5. And we've got our 1,5 relationship. So acid hydrolysis and with heat, this gets decarboxylated. So let's do this. And that's you're gonna end up adding H plus eventually. But that's basically how you can decarboxylate our diacid. You end up with your species, which has got the 1,5 relationship. So in this case, we're using the ketone, which has got the alpha beta unsaturated ketone as the Michael acceptor. Can't spell today. And our nucleophile in this case is the malonate. There are other as I said at the very start way over here, there's a number of different enolate equivalents that you can use for these types of reactions. And so for the next one, I thought I would remind everybody of a different kind, which we haven't seen recently in this class. So that was just the first one. So, but this strategy, oh, sorry, I'm going all over the place. Come on. This strategy, when you've got the 1,5 relationship, is the same in each case. We're generating an enolate or an enolate equivalent, and we're doing some type of 1,4 addition. So the one on this one, scenario A, thought I'd remind everybody that other types of enolate equivalents exist. And here is one of them. And this is our, this is the enamine. So it's similar to an enol, except for instead of having an alcohol, it's an amine. So, but if we draw a resonance structure of this, we have got something that is very similar. Again, the alpha carbon, sorry, yeah, the alpha carbon has got a negative charge. Enamines are less reactive than enolates, like let's say a lithium enolate. So it's relying on the nitrogen to push those electrons and have this as being the reactive species. But it does actually work quite well, particularly for 1,4 addition. So in this case, if we're using an ester as our acceptor, these reactions work very well. So this would go there. And we form so you generate an enolate here, and then what can happen is it's very similar. You can, I don't know if this would do it intramolecularly or if it happens, because it all depends on how, but there is a proton here which can just get grabbed. If we do this, then we end up with our, oh, sorry, this, what am I doing? It's bad news there. This. We can regenerate our enamine. Or if there's a solvent, if there's a proton in the solvent, it would just grab that. Typically you wouldn't do that with a acidic, with a product solvent though. Anyway, now, one of the things that we might not remember is that enamines or imines, because this group here is an imine. These are susceptible to, if you've got acid and water, these get hydrolyzed back to the ketone. So ketone. So we might not, if we do it, one of the ways that, if we want to go in this direction, we would use a secondary amine and moderate the pH, like the system. So the pH is around 5. You need a slightly acidic system, and that's going to take a ketone or technically an aldehyde to the enamine. And over the course of this reaction, the carbonyl is technically losing, or the amine and the carbonyl is technically losing water. We're losing a proton from this carbon here. We're losing the oxygen, and we're losing this proton here. So that's where the water comes from to generate our enamine. So an enamine is basically a masked ketone. It's just a variety of making it like nucleophilic. So this 1,5 addition combination, usually it's possible to come up with a Michael acceptor and an enolate or an enolate equivalent. So, and you can play with the yield, you can play with what you're using as your nucleophile. Is it an enamine? Is it a malonate type thing? Or are you going to just try with a regular lithium enolate and see if that works to help with each type of reaction? So yeah, this is just a super common way of generating this type of relationship. So depending upon like where the numbers are, you can, what's your nucleophile and what's your electrophile. That was basically the end of the whole retrosynthesis section. And there's a combination of, like, so two of the most powerful reactions that we've got are the 1,4 addition and using enolate equivalents. So these could be things like aldol reactions, Claisen condensations, 1,4 additions. There's a whole bunch of things that the enolates can be used for. There's a really famous synthesis that uses this cyclic diketone. And you can imagine that these two protons here are quite acidic. So you can use a base to generate the enolate. This. And you can throw in an electrophile. Let's put in methyl iodide just for the sake of it. And here we go. Now the super famous reaction is using this diketone with this guy. Methyl vinyl ketone. Sometimes abbreviated as MVE. And so this will be our, this is really neat. This is going to be our Michael acceptor. And later on, it's going to be our, it's going to become our enolate. So how would this work? Okay, so so we'll use some base, lithium, sodium hydride. Why not try it? That's my favorite. Throw in our methyl vinyl ketone. So just draw this methyl group up. Beta. This is beta. Alpha. Negative charge. Now, this, if you've got, this can be, we can convert this enolate. So if we think back to our enolates, this is basically our thermodynamic enolate here, thermo. That this can be converted into our into the kinetic enolate, and when it does, something interesting is going to happen here. So how would this happen? So this could grab, like this negative charge can grab, it can deprotonate some starting material, and then later on, the proton, like on the, so this could get converted into this. Which could get, subsequently, it could get deprotonated again to form the kinetic enolate. So like this can happen all in one pot, or you can isolate it and then do the second step. But the neat part is that in this second step, we have got the possibility of, we've got a ketone and we've got an enolate. In fact, it's a symmetrical ketone. And these go here, these electrons attack here, and the electrons move up, which will give us, so we're basically doing an aldol reaction. An intramolecular aldol reaction. And let's label this properly. O minus the methyl group. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So on carbon 4, we've got our ketone. And the very last, so you remember that the aldol reaction, if we protonate this, we end up with the corresponding alcohol. There was another thing which happened too, if you weren't careful and you just left this going over time, and that is that you can lose water. It can be dehydrated through the E1CB mechanism. And this generates this ketone here. And this is a really interesting, this is a, okay, so here we go, that's a methyl group. And this ketone here is, it's pretty much, it's a famous building block in a lot of the natural products that are that are made here. So the thing which is really, so let's just draw. This is, I'll put a methyl group here too. This structure with the three 6-membered rings and the 5-membered ring, this is the basic structure of all of the steroids. Some of them have a methyl group here, some of them don't, because sometimes this first ring is, I'll highlight this in yellow. Sometimes this first ring here is aromatic. If it's aromatic, obviously it doesn't have a methyl group. But if it's not aromatic, there is that methyl group in green here. And you'll notice that this little, this building block has got a lot of the parts that you need to, particularly this methyl group. And it's got the 2 fused 6-membered rings. And so it's a pretty famous building block that's found in a lot of syntheses that when you're looking at a lot of the classic synthetic routes that people use. Yeah, so it's just a common sort of building block, and it's a really neat reaction. So it's a Michael addition, and the corresponding enolate condenses on the ketone intramolecular, and then there's the dehydration, which gives you the double bonds. And part of the fun things which is interesting is that you've got a double bond here, which can be used to further functionalize things. And you've got a ketone here, which you can use in a number of different manners. But if you've got a ketone here, then that makes this carbon nucleophilic. And it also makes this carbon in gray, I guess. This carbon, oh, that's a bad, this carbon in gray. That becomes an electrophilic carbon if there's a double bond there. So it's a really neat little building block for a lot of the syntheses that we'll see. So yeah, that's the one thing I wanted to bring up today, was that when you do basically a 1,4 addition, and then the second step is a self-condensation, you can make some really fun cyclic structures, and they're really useful, and it's got functional groups that are important to make other bigger building blocks later on. I think that someone's actually developed a chiral way of doing this. So the addition is at this stage, let's highlight this. At this stage, this 1,4 addition here, if you can do that part chiral, so this stereocenter is fixed as RRS, put that little star there, then you actually have you've got a way of making an like one enantiomer over the other. So you've got the start of a synthesis, which would be asymmetric, I guess. And I think that addition, doing this chiral, it would require something like a chiral Lewis acid. You'd complex your ester or your ketone in some way, and then the diketone, when it's attacking, would attack on one face as opposed to the other. I can't remember this. I have to look that up. But something in my brain tells me that sort of thing has been done before. Yeah, once that stereocenter is fixed, then the rest would be fixed as well. So it's kind of neat. But that was the one thing I wanted to cover today before We do what we do on Thursday. I've got a little plan, a surprise for Thursday for everybody. I don't want to give it away. So, yeah, that was basically all I wanted to get through in today's class. Yeah, I wanted to highlight another enolate equivalent, basically the enamines. And whenever you see a 1,5 sort of system, you can disconnect. So on the alpha carbon and the beta carbon, and you'll end up with a Michael acceptor and a enolate equivalent as the nucleophilic part. Any questions at all on that? Okay, well that's easy. So we're doing there's I basically I'm gonna if I do. Does anyone care if I cut class a bit, stop class a bit early? Just because I got to get into the university to do the lab this afternoon. That's all.
No.
Plus, I think Thursday's class is going to be loaded with fun stuff. So we'll sacrifice a little bit of today for Thursday. And since everyone stayed up late doing their phys chem test, another reason to.
I appreciate you so much, Dr. Hill. I
Great.
can't even explain.
Excellent. So we'll wrap it up there, and then we've got the lab today, and we'll do that in about
An hour-ish.
an hour-ish. And it shouldn't take too long.
I didn't get a student card this year because I wasn't at the school at all first semester. I usually don't have a problem getting in, but